Okay, let's work some quick problems on molar specific heat and such. I put 10 joules of heat into 1 mole of a diatomic gas at constant volume. How much does the temperature change? All right, well, we've got an equation for that, right? The heat that flows in to a gas at constant volume is just number of moles, molar specific heat at constant volume, change in temperature. All right, so the change in temperature is just Q over NCV. All right, or if we forget that, then we say, oh, well, the change in internal energy is always N times the number of degrees of freedom over 2 times R delta T, which happens to be equal to NCV delta T. All right, and for a constant volume process, there's no work, and we know that the change in internal energy is equal to Q plus work. If there's no work, then oh, this thing we found here, change in internal energy, is just Q. And even though we forgot this equation, now we've got it back. All right, so there's our answer. I put 10 joules of heat into 1 mole of a diatomic gas at a constant pressure. How much does the temperature change? This is just like the previous problem, only now it's at constant pressure. And so we pull out our equation, Q is equal to N Cp delta T, because now we're at constant pressure, so we use the molar specific heat at constant pressure, which of course is equal to NCV plus R delta T. Anyway, we can solve this for delta T. But let's do this the hard way. Instead of doing this the easy way, let's do it the hard way. So the hard way, we're going to forget that we have this equation, all right? And we're just going to say, oh, the change in internal energy, let's go down here, the change in internal energy is always equal to N, number of degrees of freedom over 2, R, delta T, which I can write as NCV delta T, right? But this is a constant pressure process, so there is work done. So the change in internal energy, the first law of thermodynamics says I change the internal energy by putting energy in. I can put energy in with heat. I can put it in with work done on the gas. But now the work done on the gas is not zero because this is not constant volume, it's constant pressure. But for a constant pressure gas, we know that the work is just minus the integral of P dV. But for a constant pressure process, the pressure comes out, and this just becomes minus P delta V, right? And so I look at that and I say, well, what is P delta V? Well, I've got too many variables. Let's see if I can find another equation to eliminate one of them. So let's look at the ideal gas law. PV equals nRT. If I take the derivative of this side with respect to something, I don't know, whatever, I'm going to tweak something. How does this side change and how does this side change? Well, the pressure doesn't change, only the volume changes. So if I tweak something, this side will change as the change in volume, and this side, N and R are constant, so it just changes with delta T. So I go, oh, that right there, this P delta V, that's just N R delta T. Okay, so this was an aside, and we come up here and we're going to say, oh, the change in internal energy is NCV delta T, right? But that's equal to Q plus work, but work is just negative nRT, nR delta T. All right, let's solve this for Q, just for kicks, okay? Q is equal to, I bring this thing to the other side, and it's going to be N CV plus R delta T, and you look at this and you say, oh, I can solve this now for delta T, and you look at this and you say, oh, this is effectively Q is equal to N times something times delta T. This is the molar heat capacity. This is the molar specific heat at constant pressure, and that's why it's just CV plus R. We just derived that. Tricked you. Thought we were working a problem. I actually did a derivation. Okay, I'm using a piston to lift puppies from the basement to the ground level. I heat the air in the piston, it expands, and it lifts the puppies. I put 10 joules of heat into 1 mole of a monatomic gas at constant pressure. How much work is done? How much work does the gas do on the piston / puppies? All right, so I've got this piston. I put puppies on it. All right, that looks more like a cat. Make the ears floppier, I guess. All right, so we heat up the gas, the piston goes up. How much work does the gas do? All right, well, this is a constant pressure process. The piston and the puppies are always pulling down with the force of gravity, right? So It's constant pressure. That means that Q is equal to NCP delta T. All right, so I can easily find the change in temperature, but I want to know how much work is done. Well, okay. First law of thermodynamics. Change in internal energy is Q plus work. All right? Well, guess what? I've got Q. I'm given Q, so I know Q. From Q, I can find delta T. All right? But the change in internal energy is always NCV delta T. All right? So the work, then, is just going to be NCV delta T minus Q. Big Q is NCP delta T. All right, so this is just going to be N. Well, CP is CV plus R, right? So this is just negative N times R delta T. All right, and I found delta T up there. So anyway, it's just algebra at this point. Just showing you how you can use different equations to bring things together. All right, there you go.